Here is the first example. Okay, the hook is used to lift the force of 1.2 kilonewton. Determine the maximum tensile and compressive stresses at section AA. So here is our section AA. So the cross section is circular and has a diameter of 35 millimeter. So here is the cross section, and its diameter. The diameter is 35 millimeter. Okay, so let's analyze this case. As we mentioned, it's not as simple as a axial loading P, since we're not analyzing the stress here, right? If we're not analyzing the stress at this point, this cross section, it will be simple. But we're analyzing this cross section AA. Okay, so assume that we have a local centroid here. So you can see that the axis and P, or between these two, we will have a arm, right? The distance is the arm. So that this P, apart from generating a normal stress, it will also generate a bending moment to this cross section, right? So here, what is the arm? What is the value of this arm? Okay, we have given two additional sizes, D here and D here is 100 millimeter and 65 millimeter respectively. So this arm would be either 65 plus 35 over 2 or 100 minus 35 over 2. Right? So the result will be 82.5 millimeter. Right? So this is the arm. Then we can start to do the calculations following the several steps. So the first step, we'll move forces to centroid. Right? Move forces to the local centroid. As what we did here, you just move it to the centroid, then you can calculate two reaction forces. Right, this is the force. When you move it here, the P will be here, and the bending moment M will be here. So as the reaction forces, you will have F and moment M. Right. So obviously the M, the F equals P. Right, that is 1.2 kilonewton or 1,200 Newton. Right, then the M equals P times the arm. Right, that is 1,200 times 82.5. Right, you will get 99,000 Newton millimeter. Then we will calculate the section properties. Right, you may have realized that in here we will need to do two sets of calculations. One is to analyze normal stress induced by the axial loading, F or P. I just said then we'll analyze the bending stress due to the bending moment M. So you will need two section properties that are A and I. Right, so the A is just pi times 35 square over 4. Right, the 35 is the diameter of the cross section. Right, and here you get 962 square millimeter. Then how about the I? The moment of inertia would be pi 35 to the fourth over 64. Right, so you will get 73,660 millimeter to the fourth. Then, based on this loading, this reaction forces and section properties, then we can calculate the stress components. Right. So the third step, we will calculate the stresses. The first components of it will be the normal stress. Normal stress due to the axial loading, right? So the sigma 1 equals F over A. So that is 1,200 Newton over the A is 962. 962. So you will get 1.25 MPa. Is this compressive or tensile stress? Right, the F. It's positive or negative? It should be positive, right? It's an intention, right? So here you get a positive 1.25 MPa. And the second component, bending stress. Since we're requested to just calculate the maximum tensile and compressive stresses, so we just use the equation to calculate maximum stresses, right? You just use MC over I, right? MC over I. So M is 99,000. What is the C? C is the maximum distance from a point to the neutral axis, right? or to the centroid. What is that? That is the radius, right? The radius, half of the diameter, or 35 over 2. Over I, and the I is 73,660. 73,660. Okay, so here you will get 23.5 MPa. Is this in compression or tension? It depends, right? It depends on the locations, the points, right? So let's look at the left point and the right point, the right-hand side. Okay, so on the left, will it be in compression or in tension? It's a bending moment in here, right? So would that be in compression or tension? It'll be in compression, right? In compression, so that means it will be negative. Let's use a different color to note it. Okay, on the left-hand side, the stress is negative 23.5 MPa. And on the right-hand side, so it will be positive. Right? So then we can sketch them. We can sketch the combined effects of these two sets of normal stresses. Okay. Then this is the cross section. So due to the axial loading, the sigma 1 is positive. Okay, this is a tensile loading. This is a tensile loading of 1.25 MPa. And it will be combined with the stresses generated by the bending. Okay, the same cross section. It will be in compression. On the left hand side, and tension on the right hand side. Okay, so here is positive 23.5, and on the left hand side the maximum value is negative 23.5. What is the result? What is the combined effects? Okay, we have this cross section again. So because of the combination of stresses on the left side, the magnitude of the compressive stress will be increased or decreased. The magnitude will be decreased, right? So here you get a smaller value, and that is negative 23.5 plus 1.25. And on the right hand side, the magnitude of the tensile stress will be increased. Okay, and the magnitude will become positive 23.5 plus 1.25. Okay, so then we can summarize them, combine this effect. Okay, then the maximum tensile stress will be, as we analyzed above, it will be positive 23.5 plus 1.25. That will be 24.75 MPa. And the maximum compressive stress will be negative 23.5 plus 1.25. That will be negative 22.25 MPa. Okay, so that's it. We just finished with the analysis of the combined effects of the two external loading.